Good morning students. And today we are going to discuss about our second unit, infinite impulse response filter. So in the infinite impulse response filter we have normally two type of filters in your digital discrete time signal processing. First one is digital filters and another one is analog filters. So first of all we are going to see about the what are the difference between the analog filters and digital filters. So in analog filters we use the analog input and generate the analog output. In digital filters we use the digital input and we generate the digital data as output. And the analog filters will be designed with the help of active or passive electronic components, and the digital filters will be designed with the help of adders, multipliers and delay units. And analog filters is described by the differential equation, and digital filters will be represented by the difference equation. And the frequency response for analog filters can be modified by changing the components, and the frequency response of digital filters can be changing by filter coefficient. And these are some of the advantages of your digital filters. In digital filters the performance will be not changed with the common aging, temperature and power supply variation, and digital filters is highly immune to noise, and digital filters offer a wide variety of shapes of the amplitude and phase response. Digital filters can be observed over a wide range of frequencies. The coefficient of digital filters can be programmed and altered any time to obtain desired characteristics. Multiple filtering is possible only in digital filters. And in the IR filter design we already studied the two types of filters, analog filters and digital filters. In analog filters we have three different types of filters: Butterworth filter, Chebyshev filter and elliptic filters. First of all we are going to see about the Butterworth filter. So analog Butterworth filter. So first we are going to see the how to design the analog Butterworth filter. The design steps. Step number 1. From the given specification find the order of the filter n. N is always greater than or equal to log of root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1, the whole divided by log of omega s divided by omega p. We also written this n is always greater than or equal to log of lambda by epsilon divided by log of omega s divided by omega p, where epsilon is equal to root of 10 power 0.1 alpha p minus 1 and lambda is equal to root of 10 power 0.1 alpha s divided minus 1. And step 2. Round off the above, found n to its next highest integer and find the normalized transfer function omega c is equal to 1 radians per second. H of is equal to numerator polynomial divided by denominator polynomial. But for in the Butterworth filter the numerator polynomial value is always 1 and the denominator polynomial value is using this tabulation. For order 1 denominator is s plus 1, for order 2 denominator is s square plus root 2 s plus 1, and in order 3 denominator s plus 1 into s square plus s plus 1, like that. And then after finding the normalized filter transfer function, then we are going to calculate the cutoff frequency omega c. Omega c is equal to omega p divided by 10 power 0.1 alpha p minus 1 the whole power 1 by 2 n. And then we are going to calculate the original transfer function. For low pass filter h of s, where s is replaced by s by omega c, and high pass filter h of s is replaced by omega c by s. So this is a one simple problem. For given specification design an analog Butterworth filter. The specification is 0.9 less than or equal to mod h of j omega less than or equal to 1, for 0 less than or equal to omega less than or equal to 0.2 pi, and then mod h j omega less than or equal to 0.2 for 0.4 pi less than or equal to omega less than or equal to pi. For given specification omega p is equal to 0.2 pi, omega is equal to 0.4 pi, and the epsilon will be calculated with the value of 0.9. The formula is 1 by root of 1 plus epsilon square is equal to 0.9, where epsilon is equal to 0.484, and lambda will be calculated with the formula of 1 by root of 1 plus lambda square is equal to 0.2. By using the formula lambda is equal to 4.898. And find the order of the filter n. N is always greater than or equal to log of root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1, where n is always greater than or equal to log of lambda by epsilon the whole divided by log of omega s divided by omega p. N is always greater than or equal to 3.34. And then second step is rounding of the n to the next highest integer, and then we go into calculate the normalized transfer function. We already studied the numerator polynomial value is for Butterworth filter is 1, and the denominator polynomial value is calculated with the help of table, given table. So h of s equal to 1 divided by s square plus 0.76537s plus 1 into s square plus 1.8477s plus, and then we're going to calculate the cutoff frequency with the formula of omega p divided by 10 power 0.1 alpha p minus 1 the whole power 1 by 2n. With the formula we're going to calculate omega c value. The omega c value is 0.754. So the problem is the low pass filter design, so s is replaced by s by omega c. By in ha of s, the s will be replaced by s by omega c. By substituting the value we find the original transfer function value. And this is the next problem. Here we go in the given specifications are pass band attenuation 2 dB, stop band attenuation 10 dB, pass band frequency omega p is equal to 20 radians per second, and stop band frequency omega is equal to 30 radians per second. And the formula we already know, log n is always greater than or equal to log of lambda by epsilon divided by log of omega is divided by omega p. By substituting the value we get 3.37. So second we equaling the next highest integer, so is equal to 4. So we write the normalized transfer function with the help of table, and then we calculate the cutoff frequency omega c is equal to omega p divided by epsilon power 1 by n. So by substituting the epsilon value we get 21.3866. Then we write the normalized transfer function value with this given cutoff frequency, and the problem is low pass filter, so we replace s by omega c. We substitute in this value in the normalized transfer function, we get the original transfer function. Next we go for the Chebyshev filter. So Chebyshev filter we have two types already studied, type 1 Chebyshev and type 2 Chebyshev. In type 1 Chebyshev we have only the pole values, and type 2 we have poles and zeros values. And type 1 equiripple behavior in the passband, and type 2 monotonic behavior in the passband, and type 1 monotonic characteristics in stop band and equiripple behavior in the stop band. These are the some of the difference in type 1 Chebyshev and type 2 Chebyshev. This is a diagram represent differentiation. And here next we go study about the steps to design the analog Chebyshev filter. Step 1, find n. N is always greater than or equal to cos h inverse of lambda by epsilon divided by cos h inverse of omega by omega p, where n is always greater than or equal to cos h inverse of root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 the whole divided by cos h inverse of omega is divided by omega p. And then second step, round up the above founded n to its next highest integer, and using following formula find the value of a and b, which are minor and major axes of eclipse. A will be calculated with the formula of omega p is equal to mu power 1 by n minus mu power minus 1 by n by 2. B is equal to omega p mu power 1 by n plus mu power minus 1 by n by 2, and mu will be calculated by epsilon inverse plus root of epsilon inverse minus 2 plus 1, and epsilon is equal to root of 10 power 0.1 alpha p minus 1. And then we are going to calculate the poles xk. Is formula is a cos pi k plus j b sin pi k. Pi k is the angle value that will be calculated pi by 2 plus 2k minus 1 divided by 2n into pi. And then we are going to calculate the denominator polynomial of the transfer function using the above poles, and then we go for calculate the numerator of the polynomial. Numerator will be calculated with two steps. First, n is odd means we substitute s equal to 0 in the denominator polynomial and the value is equal to the numerator. For n is even means substitute s equal to 0 in the denominator polynomial and divide the result by root of 1 plus epsilon square and substitute the value to the numerator. And this is the problem. Given specification is alpha p is equal to 3 dB, alpha s equal to 16 dB, fp is equal to 1 kHz and fs equal to 2 kHz. Determine the order using the Chebyshev filter and find the h of s. So the given values are alpha p is equal to 3 dB, alpha s equal to 16 dB, and fp is equal to 1 kHz, fs equal to 2 kHz. So frequency will be given in the hertz format, that will be converted into the radians per second by using the formula omega p is equal to 2 pi fp. The value is 2000 pi radians per second, and omega s equal to 2 pi fs. The value is 4000 pi radians per second. So then we are going to calculate the order of the filter n. The formula is n is always greater than or equal to cos h inverse of root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 the whole divided by cos h inverse of omega s by omega p. By substituting the value we get n is always greater than or equal to 1.912. So round up to the next highest integer, so the n is value is 2. and then we're going to calculate the a value by using the formula alpha p into mu power 1 by n minus mu power minus 1 by n by 2. By calculating a value, we know the value of mu. Mu will be calculated by epsilon inverse plus root of epsilon power minus 2 plus 1. So we're going to calculate mu value means first we're going to calculate the epsilon value. Epsilon is nothing but root of 10 power 0.1 alpha p minus 1. So by calculating these and all, mu value is 2.41, and then we calculate the a value by using the mu and epsilon values. So the a value is 911 pi, and then the b will be calculated by the formula of mu p omega p mu power 1 by n minus mu power minus 1 by n by 2. So by substituting mu values and omega p value, we get 2198, and then we are going to calculate the poles of the filter. Poles will be calculated by the formula of a cos pi k plus b j b sin pi k, and the pi 1 and pi 2 will be calculated with the formula of pi by 2 plus 2k minus 1 by 2n into pi. So by substituting the value, we get pi 1 is equal to 3 pi by 4 and pi 2 is equal to 5 pi by 4. So S1 value is minus 644.17 pi plus J 1554.20, and S2 value is minus 644.17 pi minus J 1554.20, and the denominator will be calculated by using the above pole values, and then we are going to calculate the numerator value. Here the order of the filter is even, so the numerator will be calculated by substituting s equal to 0 in the denominator polynomial, and the value will be divided by root of 1 plus epsilon square. By using this formula, we get the numerator value that will be substituted in your transfer function.